Hoover Dam will not collapse in an explosion. There will be no cracking concrete, no sirens echoing through Black Canyon, no cinematic disaster broadcast across the American Southwest. If Hoover Dam ever stops producing electricity, it will happen quietly. It will happen because of a number, 950 feet above sea level. That is minimum power pool, the elevation at which the turbines inside Hoover Dam can no longer generate hydropower. Below that level, the hydraulic head becomes insufficient to spin the generators. The blades slow, the hum inside the powerhouse fades. Not because of politics, not because of funding, because of physics. And for nearly 90 years, that number felt distant and theoretical. Today, it is tracked, modeled, and discussed in rooms that understand exactly what it represents. Stand on the crest of Hoover Dam in early 2026 and nothing appears unstable. Tourists lean over the railings with their phones raised. The turbines spin steadily beneath the concrete arch. The structure looks permanent, immovable, engineered to outlast generations. The dam feels eternal. Yet beyond the concrete, across the canyon walls of Lake Mead, a stark white mineral band wraps around the red rock like a scar. The bathtub ring marks where the water once stood during wetter decades. At full pool, Lake Mead reaches approximately 1,229 feet above sea level. Today, the reservoir sits more than 100 vertical feet below that mark. That missing water is not symbolic. It is visible from space. It is etched into stone. It represents something far more important than scenery. It represents margin. Hydroelectric dams operate according to geological reality. Water stored at elevation creates pressure as it moves downward through turbines. Engineers call the vertical distance between the lake surface and the turbine's hydraulic head. When Lake Mead is high, Hoover Dam has abundant hydraulic head. Abundance means flexibility. When electricity demand spikes during extreme heat, operators can release additional water and increase output within minutes. As the reservoir drops, hydraulic head shrinks. The turbines continue to spin, but their ceiling lowers. The system becomes less forgiving. Infrastructure rarely fails the moment it weakens. It fails when reduced margin meets stress. To understand why this shift matters, you have to step back more than a century before Hoover Dam existed, before the neon lights of Las Vegas reflected off desert rock. In 1905, the Colorado River broke through irrigation structures and flooded California's Imperial Valley for nearly 2 years. Farmland was destroyed. Communities were displaced. The river behaved exactly as rivers have for millions of years, responding to snowpack, precipitation, gravity, and terrain. For a rapidly expanding nation, unpredictability was unacceptable. The solution was control. Congress authorized the Boulder Canyon Project in 1928. Construction began in 1931 during the Great Depression. More than 20,000 workers labored in extreme desert heat, blasting diversion tunnels through canyon walls and pouring millions of cubic yards of concrete. When Hoover Dam was completed in 1935, it stood 726 feet tall, at that time the tallest dam in the world. Behind it, Lake Mead began filling. At full capacity, the reservoir could store approximately 26 million acre-feet of water, nearly 2 years of average river flow under early 20th century conditions. That storage reshaped the Southwest. It provided flood control, reliable irrigation, and hydropower generation. It enabled cities like Las Vegas and Phoenix to expand into major metropolitan regions. It supported agriculture across Arizona and California. Hoover Dam became more than infrastructure. It became a symbol of certainty in an arid landscape defined by variability. For decades, the system appeared resilient. Wet years filled the reservoir. Dry years lowered it, but levels rebounded. The expectation of recovery became embedded in planning. Around the year 2000, Lake Mead stood near modern-era highs. In the years that followed, the reservoir entered a prolonged period of tightening. There were temporary rebounds during strong snowpack winters, but the overall trend narrowed. Tree ring reconstructions now indicate that the Colorado River Basin is experiencing one of its driest sustained multi-decade periods in at least 1,200 years. The river has not disappeared, but its baseline appears different from the century that shaped modern assumptions. The Colorado River originates as snowpack in the Rocky Mountains. Winter storms deposit snow at high elevation. Spring melt feeds tributaries that eventually flow into Lake Powell and then downstream into Lake Mead. The system depends on snow accumulation, temperature patterns, soil moisture, and runoff efficiency. Warmer winters alter precipitation form. Earlier melt shifts runoff timing. Drier soils absorb more water before it reaches reservoirs. Rising temperatures increase evaporation across Lake Mead's vast surface area. None of these processes are dramatic in isolation. Together, they reshape long-term water availability. Layered on top of hydrology is law. The Colorado River Compact of 1922 divided water among 7 states based on flow measurements gathered during one of the wetter stretches of modern record. Those allocations became binding agreements. For decades, reservoir storage masked any imbalance between allocated demand and actual long-term average flow. Lake Mead acted as a buffer, but buffers are not infinite. If long-term inflows remain lower than total demand, storage declines. Upstream, Lake Powell behind Glen Canyon Dam forms the other half of the system. For decades, Powell and Mead operated in coordinated balance. In dry years, Powell could release additional water to stabilize Mead. In recent years, strategic releases from Powell have slowed Mead's decline, but transferring water between reservoirs does not create new supply. It redistributes stress. When both reservoirs experience prolonged tightening simultaneously, flexibility diminishes across the entire system. The margins shrink from both directions. If you care about how geology quietly shapes the world we build on top of it, from volcanoes and faults to rivers and reservoirs, this is what we break down here. Subscribe so you don't miss the next deep dive. Because when geological systems tighten, engineered systems feel it next. Now, consider what that means for electricity. Hoover Dam historically generates billions of kilowatt hours annually, supplying utilities across Nevada, Arizona, and California. Hydropower's strength lies in responsiveness. Imagine a July evening in Las Vegas with temperatures exceeding 110 degrees. Air conditioning runs continuously. Solar generation declines with sunset. Demand spikes during the evening ramp. Hydropower can respond quickly, releasing water and increasing output within minutes. As Lake Mead declines, maximum generating capacity narrows. The dam still operates, but its surge capability shrinks. That does not mean immediate blackout. It means thinner margins during extreme conditions. The Southwest today is far larger than in 1935. Tens of millions depend on the Colorado River system directly or indirectly. Agriculture across Arizona and California generates billions annually. Urban infrastructure and industrial corridors rely on water and power stability, yet much of this system was built during a relatively wet century. If the 20th century represented a hydrologic high relative to longer-term averages, then current conditions may represent recalibration rather than anomaly. The number 950 feet remains the threshold for minimum power pool. Lake Mead remains above that elevation. But the fact that this number is routinely modeled reflects a psychological shift. For decades, few imagined the reservoir approaching levels that constrain hydropower. Today, shortage tiers trigger automatic reductions when specific elevations are crossed. Water managers renegotiate allocation frameworks. Municipal systems expand recycling. Conservation becomes structural rather than temporary. Hoover Dam's concrete remains sound. Its turbines are operational. The variable is not structural failure, but geological reality. Rivers respond to snowpack. Snowpack responds to atmospheric circulation. Reservoirs respond to cumulative balance. The white bathtub ring around Lake Mead is not a countdown clock to collapse. It is a geological record of shifting baseline conditions. It marks the difference between expectation and present measurement. If Lake Mead approaches minimum power pool in the coming decades, the adjustment will not be explosive. It will be administrative, financial, and structural. Energy portfolios will shift, water agreements will evolve, infrastructure investments will adapt. The dam will remain a marvel of engineering, but it will also stand as a reminder that human systems operate within Earth systems. The turbines spin today, the generators hum. The line remains above 950 feet. But the margin between current elevation and that threshold is narrower than it once was. In arid environments, margin equals security. Hoover Dam does not negotiate with arithmetic. Water in versus water out, elevation versus pressure, allocation versus supply. These are measurable relationships. The story unfolding at Lake Mead is not one of immediate catastrophe. It is one of gradual recalibration. The American West is not collapsing. It is adjusting to hydrology that may more closely resemble long-term geological averages than the relatively wet century that enabled rapid growth. Cities will adapt. Agriculture will evolve. Energy systems will diversify. But the illusion of endless margin fades. Hoover Dam will not fail in spectacle. It will respond to gravity, snowpack, evaporation, and time. The turbines still spin. The river still flows. But the next measurement is always being recorded, and geology always keeps the final ledger.